This video will show you how to set up a Comsol model with a one-dimensional flow through porous media under axisymmetric conditions. So set up an axisymmetric model and go to fluid flow and select single phase flow or porous media flow and Darcy's law. Add that physics and then add a study that's stationary. It's a 1D geometry, so we'll set up an interval and we'll go from 0.1, radial distance of 0.1 to radial distance of 1000. Go ahead and build all objects. There's the geometry. And for definitions, we have a variety of definitions we want to use. I've set them up in a file, so you need to import this file. Go to the folder and search for time variables.txt. Import those. And here are the variables. The variable name is on the left and the expression is on the right. So now we'll set up the Darcy law physics. Go to porous medium fluid. We'll assume that it's water that has a density of rho 1. Rho 1 is the variable name that we use for the density of water. So we could put in 1,000 kilograms per cubic meter, or we could type in the variable name rho 1. Under dynamic viscosity, we'll just use this built-in value here, 10 to the minus 3 Pascal seconds. Now the porosity, we didn't put the porosity as a variable, so we have the hydraulic conductivity, but we didn't put the porosity, so we just need to type the value in. It's 0.1. And then we need to set up the hydraulic conductivity. The default is permeability, so switch it to hydraulic conductivity in units of meters per second. And that's a variable called capital K that we set up in the definition variable right there. Yep, there's the hydraulic conductivity. So we'll have a pressure boundary condition out of the far 1,000 meters out, pressure of 0. And the inner boundary condition will be an inlet condition where we specify the flux at the well face, and that's a variable called well flux that we've already set up. So we'll just type in that variable name. And that sets up the physics. And we'll set up the mesh. This is just a one-dimensional mesh. And the default might be OK. That's kind of a coarse mesh, so we'll add a few more elements. We'll give it 50 elements along that length, evenly spaced. And now we'll go and compute the result. There's the result. There's what it looks like. Actually, the previous results have been updated. This is what it should look like. The hydraulic head, it's about minus 11 meters at the well. And now we're going to add in the analytical solution. This is the time solution. And there's the expression up there at the top, and the arguments that we're going to pass into it are those three variables, Q term, R, and R influence. And we're going to call it with a name called time 2. So we type this in the analytic expression. This is a function that we can now use, and we're going to plot this. Going to the plot, add a line graph, and then I'm going to call this function. It's called time 2, and the arguments are there. And then I should be able to plot this. And this is on a semi-log plot. You can see the green line is the analytical solution. They're very close on if we use Cartesian semi-log, you can see a little bit of difference at small values of R, and that's because the grid is fairly coarse. I'm going to make these lines a little bit thicker so that we can see them a little bit better. Make that one dashed and make this one solid. Just change the line thickness down here under coloring and style.